Now, in this lecture, we'll find out the area of the green shape. In the drawing, we have a quarter circle. AOB is a quarter circle. And we also have tangent QP. This is tangent QP. That is tangent to this quarter circle here at this point. And we also know that line segment BQ equals to 3 units. Line segment AP equals to 6 units. This is angle BQP, that is a right angle, and this is angle APQ, that is also a right angle. Again, our mission is to find out the area of this green shape. So first of all, we define the point of tendency of tangent QP with this quarter circle. This point is point S. And we'll join points O and S together by a straight line. So what is the definition of line segment OS? Line segment OS starts from point O, that is the center of the quarter circle, and ends at point S, that is a point on the quarter circle itself. This is exactly the definition of a radius. So OS is the radius of the quarter circle, we will define the radius of the quarter circle as x. Therefore, OS equals to x, it is the radius of the quarter circle. Here you can implement rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle, and we also have tangent AB. This is tangent AB. That is tangent to this circle at this point, point M. Point M is the point of tendency. And we also have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OS of the quarter circle that is drawn to point S, that is the point of tendency of tangent QP with this quarter circle. And whenever you have a radius that is drawn to the point of tendency, then tangent QP will be perpendicular to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say, from point B, we will do perpendicular on OS. Again, from point B, we will do perpendicular on OS, on the radius OS. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in OS as M. So inside the small quadrilateral MBQS, inside this small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth missing angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this missing fourth angle must be equal to 90 degrees in its size. So inside quadrilateral MBQS we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral MBQS as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MBQS, side BQ must be equal to the opposite side MS. But BQ equals to 3, therefore MS must be also equal to 3 units in its length. So I write it down. MS equals to 3 units. We also have the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle BMQS, side BQ is parallel to the opposite side MS. BQ is parallel to MS. So I write it down. In rectangle BMQS, side BQ must be parallel to the opposite side, side MS. Repeat again. In rectangle BMQS, side BQ must be parallel to the opposite side, side MS. OS is the radius of the quarter circle. So OS is a radius, it must be a straight line. Again, OS is a radius, it must be a straight line. Okay, so OS is a straight line, and we know that part of the straight line OS that is actually MS is parallel to BQ. So part of the straight line OS is parallel to BQ, therefore the straight line OS itself must be also parallel to BQ. So I will write it down. The straight line OS itself must be also parallel to BQ. So actually in quadrilateral OBQS, in this quadrilateral OBQS, side OS is parallel to side BQ. Okay, side OS is parallel to side BQ, therefore quadrilateral OBQS is a trapezoid. So I write it down. Quadrilateral OBQS is a trapezoid. Actually, the definition of a trapezoid is a quadrilateral with one pair of parallel sides. So in this quadrilateral OBQS, side OS is parallel to side BQ, therefore quadrilateral OBQS is a trapezoid. Okay. What is the length of line segment OM? From the drawing it is very easy to see that OM equals to OS minus MS. Again, OM equals to OS minus MS. So I write it down. OM equals to OS minus MS. So OM equals to OS. OS is the radius of the quarter circle that is equal to X according to our definition, minus MS. MS equals to 3. So in conclusion, we found out that the length of line segment OM is X minus 3. So I write it down. OM equals to X minus 3 units in its length. In the next step, we will do another construction, that is to say, from this point A, we will do perpendicular on OS. Again, from point A, we will do perpendicular on OS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as N. So by doing this construction, we actually created here quadrilateral ANSP. Inside this quadrilateral ANSP, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral ANSP, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral ANSP as a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So the rectangle ANSP, side AP equals to the opposite side NS. But AP equals to 6, therefore NS must be also equal to 6 units in its length. So I write it down. NS equals to 6 units in its length. We have also the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle ANSP, side NS is parallel to the opposite side AP. So I write it down. In rectangle ANSP, side AP is parallel to the opposite side, side NS. Repeat again. In rectangle ANSP, side AP is parallel to the opposite side, side NS. But this side NS is part of the straight line OS. Again, side NS is part of the straight line OS. So if part of the straight line OS is parallel to AP, then the straight line OS itself must be also parallel to AP. So I write it down. The straight line OS itself must be also parallel to AP. So OS is parallel to AP. So in quadrilateral OSPA, OS is parallel to AP. Therefore, quadrilateral OSPA is a trapezoid. So I write it down. Quadrilateral OSPA is a trapezoid because it has one pair of parallel sides. Side OS is parallel to side AP in quadrilateral OSAP. Therefore, quadrilateral OSPA is a trapezoid. So we actually found out that quadrilateral OBQS is a trapezoid and quadrilateral OSPA is also a trapezoid. The big shape AOBQSP consists of those two trapezoids, trapezoid OBQS and trapezoid OSPA. So the sum of the areas of those two trapezoids will be equal to the area of the whole shape in total. So in conclusion, we found out that the area of the whole shape APAOBQSP is equal to the sum of the areas of the two trapezoids. Okay, so I write it down. The area of the whole shape OBQ SPA, the area of this whole shape is equal to the sum of the areas of the two trapezoids. Why? Because this whole shape consists exactly those two trapezoids, trapezoid OBQS plus trapezoid OSPA. Okay. So, what is the length of line segment ON? From the drawings, it's very easy to see that ON equals to OS minus NS. Again, ON equals to OS minus NS. So I write it down. ON equals to OS minus NS. So ON equals to NOS. OS is the radius of the quarter circle that is equal to X minus NS. We already found out that NS equals to 6. So in conclusion, we found out that the length of line segment ON is equal to X minus 6. So I write it down. This line segment ON is equal to X minus 6 units in its length. In the next step, we'll focus on this right triangle AON. So, and we'll define angle AON, this angle is alpha. So, in the right triangle AON, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing third angle here must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. So the missing angle here equals to 90 degrees minus alpha. So we'll define 90 degrees minus alpha as beta. Therefore, the missing angle here must be equal to beta. Here we have the equation 90 degrees minus alpha equals to beta. We will add to this equation alpha, and then we'll subtract beta, and we'll get that 90 degrees minus beta equals to alpha. Okay, 90 degrees minus beta equals to alpha. What is the size of this missing angle? What is the size of the missing angle? Angle BOM. The size of the missing angle BOM, this missing angle, will be equal to the big angle AOB, that is a right angle, it is equal to 90 degrees, minus this angle alpha. Again, 90 degrees minus alpha equals to this missing angle. So this missing angle equals to 90 degrees minus alpha. But according to our definition, 90 degrees minus alpha equals to beta. Therefore, the missing angle here equals to beta. The next step, we'll focus on the right triangle, triangle OBM. On the right triangle, triangle OBM, this angle equals to beta, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus beta. Okay. Why 90 degrees minus beta? Because 90 degrees minus beta plus beta is 90 degrees. And 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. So the missing angle here equals to 90 degrees minus beta. But 90 degrees minus beta equals to alpha. So the missing angle here equals to alpha. What is the length of line segment OB? Line segment OB starts from point O, that is the center of the quarter circle, and then at point B, that is a point on the quarter circle itself. This is exactly the definition of a radius. Therefore, line segment OB is the radius of the quarter circle, that is equal to x according to our definition. So OB equals to x. What is the length of line segment OA? Again, line segment OA starts from point O, that is the center of the quarter circle, and then at point A, that is the point on the quarter circle itself. Therefore, OA is also the radius of the quarter circle, that is equal to x. In the next step, we'll prove that those two right triangles can go into each other. That is to say, we'll prove that the right triangle ONA, this right triangle, can go into this right triangle, triangle OMB. So I write it down. We'll prove that the right triangle ONA, this right triangle, can go into the right triangle OMB. So, why those two right triangles can go into each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this is angle ONA. In the right triangle ONA, and it is equal to this angle, it is actually angle OMB in the right triangle OMB. Repeat again. Angle ONA in the right triangle ONA equals to angle OMB in the right triangle OMB. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles, they are both equal to alpha, therefore they are equal to each other. So this is angle NOA in the right triangle ONA, and it is equal to this angle, it is actually angle OBM in the right triangle OMB. So repeat again. Angle NOA in the right triangle ONA equals to angle OBM in the right triangle OMB. They are both equal to alpha, therefore they are equal to each other. Those two angles, they are both equal to beta, therefore they are equal to each other. So actually this is angle OAN the right triangle ONA, and it is equals to this angle. This is actually angle BOM in the right triangle OMB. So repeat again. Angle OAN in the right triangle ONA equals to angle BOM in the right triangle OMB. They are both equal to beta, therefore they are equal to each other. So actually all the triangles of the right triangle, this right triangle ONA are correspondingly equal to all the triangles of this right triangle OMB. Therefore, and finally, side OA of the right triangle ONA is equal to side OB of the right triangle OMB. They are there of the circle of the quarter circle that is equal to x, therefore they are equal to each other. So I write it down. Side OA equals to side OB. Repeat again. Side OA of the right triangle ONA equals to side OB of the right triangle OMB. They are both the radii of the circle that is equal to x, therefore they are equal to each other. So we actually found that the right triangle ONA congruent, this is the sign of congruent, to the right triangle OMB according to angle side angle rule. So what is angle side angle rule? If you prove, actually angle side angle rule is that if you prove the two angles and the side that included between the two angles in one triangle are correspondingly equal to two angles, and the side that is included between the two angles in a second triangle, then you actually proved that the two triangles can go into each other according to angle side angle rule. Here we proved that those two angles alpha and beta and the side that included between those two angles that is side OA in the right triangle ONA are correspondingly equal to those two angles that are also alpha and beta, and the side that included between those two angles that is side OB in the right triangle OMB. Therefore we actually proved that those two right triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude that side ON in the right triangle ONA is equal to side BM in the right triangle OMB. So I write it down. We conclude that side ON equals to side BM. Repeat again. We conclude that side ON in the right triangle ONA is equal to side BM in the right triangle OMB. According to the rule, these corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say ON and BM, must be also equal to each other. But we have already found out that ON equals to x minus 6. Here ON equals to x minus 6. So you can write here that ON equals to x minus 6. And from this equation, x minus 6 equals to ON equals to BM, we will derive that BM is also equals to x minus 6 units in its length. So I write it down in the original drawing. Here, this is side BM, and it is equals to x minus 6 units in its length. Likewise, because of the fact that those two right triangles can go into each other, we conclude that side OM in the right triangle OMB is equal to side AN in the right angle AON. So I write it down. Side OM equals to side AN. Repeat again. From the fact that the right angle ONA is congruent to the right angle ONB, we conclude that side OM in the right triangle ONB is equal to side AN in the right angle ONA according to the sum rule that corresponding sides in congruent triangles are equal to each other. But we have already found out that OM, this is side OM is equal to x minus 3 units in its length. Again, OM equals to x minus 3 units. So we can write here that OM is equal to x minus 3. And for this equation, x minus 3 equals to OM equals to AN. We will derive that AN is also equal to x minus 3 units in its length. This is side AN, and it is equal to x minus 3 units in its length. In the next step, I'll copy the right angle ONA, this right angle ONA in a new page, and we'll implement on this right angle ONA the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. We just right now found out that side AN equals to x minus 3 units in its length. We have already found out that ON equals to x minus 6 units in its length. And finally, the hypotenuse OA equals to x. It is also the radius of the quarter circle. So this is the right angle ONA that I copied from the original drawing. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OA, therefore the square of the hypotenuse is OA squared, and it must be equal to ON squared plus NA squared. OA equals to x, therefore OA squared is x squared, and it is equals to ON squared. ON equals to x minus 6, therefore ON squared equals to x minus 6 squared plus NA squared. NA equals to x minus 3, therefore NA squared equals to x minus 3 squared. In conclusion, we found out that x squared equals to x minus 6 squared plus x minus 3 squared. So we will open the brackets on this side of the equation, and we will get that x squared equals to x minus 6 squared. X minus 6 squared equals to x squared plus 6 squared, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 squared. X minus 3 squared equals to x squared plus 3 squared, that is 9, minus 2 times x times 3, that is minus 6x. So here we have x squared on both sides of the equation, so x squared will get cancelled. After we cancel x squared, in this side of the equation we left with nothing, that is to say 0. That is equals to, in the other side of the equation, we have 36 plus 9, that is 45. And we also have minus 12x. Minus 6x is minus 18x plus x squared. So in conclusion, found out actually that x squared minus 18x plus 45 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 18x plus 45 equals to 0, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. Now we put the data for our specific quadratic equation inside this general formula in order to find out the values of x. X is the radius of the quarter circle. So according to this general formula, x will be equal to minus b. b is minus 18, therefore minus b is minus 18, that is plus 18 plus minus square root of b squared. b is minus 18, so b squared is minus 18 squared, that is 324 minus 4 times a. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c, that is 45. So minus 4 times 45 is minus 180 divided by 2a. a is 1, so 2 times a is 2 times 1, that is 2. So in conclusion, we found out actually that x equals to 18 plus minus the square root of 324 minus 180 is 144 divided by 2. So x equals to 18 plus minus the square root of 124 is 12 divided by 2. So here we will have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12 over 2. 18 plus 12 is 30, and 30 over 2 is 15. So the first solution for x is that x equals to 13 units in its length. The radius of the quarter circle, that is x, it is equal to 15 units in its length. And we have also a second solution that is possible for x. The second solution for x is that x equals to 18 minus 12 over 2. 18 minus 12 is 6, and 6 over 2 is 3. So according to the second solution, x equals to 3 units in its length. But this solution is incorrect solution. It is actually impossible that x will be equal to 3. Why? Because of the fact that the length of this side BM, it is equal to x minus 6. Again, the length of side BM is x minus 6 units. And because of the fact that we are talking about a length must be a positive number. So we know that the length of line segment BM is x minus 6. So the length x minus 6 must be a positive number. that is to say x minus 6 must be greater than 0 because it is a positive number. If x minus 6 is greater than 0, we can add 6 to this equation, to this inequality, and we get that x must be greater than 6. We actually found out that x, the radius of the quarter circle, must be greater than 6 units. If x must be greater than 6 units, it can never be equal to 3, that is less than 6. So we can set this solution, and we left only with the second solution that is possible, with the first solution that is possible for x, that is to say x, that is the radius of this quarter circle, equals to 15 units in its length. X equals to 15. So actually, OB is the radius of the quarter circle that is equal to x, that is equal to 15. OA equals to x, that is 15 units. In this rectangle NSPA, SP equals to x minus 3. X is 15, x minus 3 is 12. So SP equals to 12 units in its length. In rectangle BMSQ, QS equals to x minus 6. X is 15, therefore 15 minus 6 is 9. So QS equals to 9 units in its length. Okay? And finally, OS is also the radius of the quarter circle that is equal to x, and x equals to 15. In the next step, I present to you the formula for the area of any trapezoid. I repeat again that a trapezoid is a quadrilateral with one pair of parallel sides. So this quadrilateral ABCD, this is quadrilateral ABCD. We know that AD is parallel to BC, and for that reason, quadrilateral ABCD that has one pair of parallel sides is a trapezoid. The two parallel sides, that is to say AD and BC, are defined as the bases of the trapezoid. So the first base is AD, and the second base is BC. So what is the area of this trapezoid? Trapezoid ABCD. The area of trapezoid ABCD equals to the sum of its bases, that is to say it is AD plus BC. Times the height over 2. The height must create 90 degrees with the two bases. Again, the height must create 90 degrees with the two bases. The first base is AD and the second base is BC. So if side CD creates 90 degrees if the two other bases, that is to say if this angle equals to 90 degrees and this angle equals to 90 degrees, then the height is CD. But if CD doesn't create 90 degrees with the two other bases, we just draw perpendicular on BC, and the perpendicular on BC will be also perpendicular to AD. Why? Because AD is parallel to BC, and the perpendicular will be the height to the base. In conclusion, found out that the area of trapezoid ABC that could be any triangle equals to the sum of its bases, that is AD plus BC, times the height over 2. The height to the base must create 90 degrees with the two bases. Okay? So what is the area of this green shape? The area of the green shape equals to the whole area of shape AOBQSP minus the area of this quarter circle AOB. Again, the whole area of the big shape AOBQSP minus the area of the quarter circle AOB will be equal exactly to the area of the green shape. So I will write it down. The area of the green shape equals to the whole area of this shape, that is shape AOB QSP. So the area of the whole shape AOB QSP minus the area of quarter circle AOB minus the area of the quarter circle AOB. So the area of the green shape equals to the area of the whole shape, the big shape AOB QSP minus the area of the quarter circle AOB. The area of the whole shape minus the area of this quarter circle AOB will be equal exactly to the area of this green shape. And we have already found out actually that the area of the whole shape OBQSP is equals to the sum of the areas of the two trapezoids. So the area of the whole shape OBQSPA is equals to the area of trapezoid OBQS plus the area of trapezoid OSPA. Why? Because of the fact that this whole shape OBQSPA consists of those two trapezoids, trapezoid OBQS plus trapezoid OSPA. Okay. So the area of the whole shape equals to the area of trapezoid OBQS plus the area of this trapezoid OSPA. Repeat again, the area of the whole shape AOBQSP equals to the area of trapezoid OBQS plus the area of trapezoid OSPA. And we subtract from the area of the whole shape the area of this quarter circle AOB minus the area of the quarter circle AOB. So what is the area of trapezoid OBQS? What is the area of this trapezoid? Trapezoid OBQS. The area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height to the bases. The height creates 90 degrees with the bases. So QS creates 90 degrees with base BQ and base OS. Therefore QS is the height to the base. So the height is QS over 2. Again, the area of trapezoid OBQS equals to the sum of the bases, that is BQ plus OS, times the height to the bases, that is QS over 2. So BQ is 3, OS is 15. BQ is 3 and OS is 15. The height QS is 9. Divided by 2. So the area of trapezoid OBQS equals to 3 plus 15, that is 18. 18 over 2 is 9, and 9 times 9 is 81. In conclusion, we found out that the area of trapezoid OBQS equals to 81 square units plus the area of trapezoid OSPA. What is the area of this trapezoid OSPA? The area of trapezoid OSPA equals to the sum of its, the length of the sum of its bases, that is OS plus AP, times the height to the bases. SP is the height because it creates 90 degrees with the two bases. Those two angles equals to 90 degrees. So times the height, that is SP over 2. Again, the area of trapezoid OSPA equals to the sum of its bases, that is OS plus AP, times the height, that is SP over 2. OS is 15 plus AP is 6. SP is 12 over 2. So the area of trapezoid OSPA equals to 15 plus 6 times 12 over 2. 15 plus 6 is 21. 12 over 2 is 6. 21 times 6 is 126. In conclusion, we found out that the area of trapezoid OSPA is equals to 126 square units. Okay? Minus the area of the quarter circle AOB. The area of this quarter circle AOB equals to the area of the circle over 4. The area of a circle with radius x is pi x squared, and pi x squared over 4 is the area of the quarter circle. X is 15, therefore x squared is 15 squared, that is 225. Therefore, the area of the quarter circle equals to 225 pi over 4 square units. 225 pi over 4 square units. This is equals to 176.716 square units. So, the area of the green shape equals to the sum of the areas of the two trapezoids, that is 81 plus 26, that is 207. That is to say, the sum of the areas of those two trapezoids, that is actually the area of the whole shape in total, is 207 square units, minus the area of the quarter circle, that is 176.716 square units. So 207 minus 176.716 is equals to 30.285 square units. So in conclusion, found out that the area of the green shape is equal to 30.285 square units. And that is the answer to the question. I'll repeat again. The area of this green shape equals to 30.285 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So, in the drawing, we have a quarter circle, AOB is a quarter circle, and we also have tangent QP. This is tangent QP, this is tangent to this circle at this point. In addition, we have line segment BQ is equal to 3 units, line segment AP equals to 6 units. This is angle BQP, this is a right angle, and this is angle AP. It is also a right angle. Again, our mission was to find out the area of this green shape. So, first of all, we defined the point of tendency of tangent QP with this quarter circle. This point is point S. Then we join points O and S together by a straight line. Point O is the center of the quarter circle. Point S is the point on the quarter circle itself. Therefore, OS is the radius of the quarter circle. We define the radius of the quarter circle as x. Therefore, OS equals to x. It is the radius of the quarter circle. We have implemented here rule 1. We have the radius OS that is drawn to point S, that is the point of tendency of tangent QP with this quarter circle. And whenever you have a radius that is drawn to the point of tendency, then tangent QP will be perpendicular to the radius FO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Okay, in the next step, we did a construction. That is to say, from point B, we draw perpendicular on OS. Again, from point B, we draw perpendicular on OS. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OS as M. By doing this construction, we created the small quadrilateral BMSQ. Inside this small quadrilateral BMSQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth missing angle. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its size. So inside the small quadrilateral BMSQ, we have 4 right angles. Any quadrilateral that has 4 right angles must be a rectangle if not a square. So we will relate to this quadrilateral BMSQ as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So in rectangle BMSQ, side BQ equals to the opposite side, side MS. But BQ equals to 3, therefore MS must be also equal to 3 units in its length. Likewise, we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle BMSQ, side BQ is parallel to the opposite side MS. I'll repeat again. In rectangle, the small rectangle BMQS, side BQ is parallel to the opposite side, side MS. BQ is parallel to MS. OS is the radius of this quarter circle. OS is a radius, it is absolutely a straight line. So OS is a straight line. OS is a straight line, and we have part of the straight line OS that is MS is parallel to BQ. So if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, the straight line OS itself must be also parallel to BQ. The straight line OS must be also parallel to the straight line BQ, or OS is parallel to BQ. OS is parallel to BQ. So in quadrilateral OBQS, side OS is parallel to the opposite side BQ. And for that reason, quadrilateral OBQS is a trapezoid. Quadrilateral OBQS is a trapezoid because it has one pair of parallel sides. And the definition of a trapezoid is a quadrilateral with one pair of parallel sides. What is the length of line segment OM? From the drawing it is very easy to see that OM equals to OS minus MS. Again, OS minus MS equals to OM. Again, OM equals to OS minus MS. So OM equals to OS, that is X, that is the radius of the quarter circle, minus MS, that is 3. So we're going to find out that the length of this line segment OM is X minus 3. OM equals to X minus 3. In the next step we did another construction, that is to say from point A we draw perpendicular on OS. Again, from point A we draw perpendicular on OS, the radius OS. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS, this point as M. As N. Okay? By doing this construction, we created quadrilateral ANSP. Inside quadrilateral ANSP we have 1, 2, 3 rectangles. Therefore, the fourth missing angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral ANSP we have 4 rectangles. Any quadrilateral that has 4 rectangles must be this rectangle in front of square. So we relate to this quadrilateral ANSP with 4 rectangles as a rectangle. So in rectangle ANSP, the opposite sides must be equal to each other. That is to say, side AP must be equal to the opposite side NS. But AP equals to 6, therefore NS must be also equal to 6 units in its length. Here, NS equals to 6 units in its length. Likewise, the opposite sides of a rectangle are parallel to each other. So AP, in rectangle ANSP, side AP must be parallel to the opposite side NS. AP must be parallel to NS. So I repeat again. In rectangle ANSP, side AP must be parallel to the opposite side NS. So AP is parallel to NS. But NS is part of the straight line OS. So we know that part of the straight line OS is parallel to AP. Therefore the straight line OS itself must be also parallel to AP. Okay? The straight line OS itself must be also parallel to side AP. So OS is parallel to AP. So in quadrilateral AOSP, in this quadrilateral, we know that side OS is parallel to side AP. Therefore, this quadrilateral AOSP is a trapezoid. Why? Because it has one pair of parallel sides. Repeat again, quadrilateral OSPA is a trapezoid. So, we already found out that quadrilateral OBQS is a trapezoid, and we just right now found out that quadrilateral OSPA is also trapezoids. The big shape OBQSPA consists of those two trapezoids. And therefore the sum of the areas of the two trapezoids must be equal to the area of this shape, the whole shape, OBQSPA, because it consists of those two trapezoids. Repeat again. The area of the whole shape, OBQSPA, is equals to the sum of the areas of the two trapezoids. The area of trapezoid OBQS plus the area of trapezoid OSPA. Okay? Then we found out the length of this line segment ON. From the drawing it is very easy to see that ON equals to OS minus NS. Again, ON equals to OS minus NS. Here, ON equals to OS minus NS. So ON equals to OS, that is X, that is the radius of the quarter circle, minus NS. NS is 6. So we found out that the length of this line segment ON is X minus 6. Then we focus on this right angle AON. In the right angle AON, we define this angle as alpha. So in the right angle AON, this angle equals to alpha. this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So the missing angle here must be equal to 90 degrees minus alpha. We defined 90 degrees minus alpha as beta, therefore the missing angle here must equals to beta, according to our definition. Okay? Here, we have the equation 90 degrees minus alpha equals to beta. If we add to this equation alpha and then subtract beta, we get that 90 degrees minus beta equals to alpha. Then, we found out the size of this missing angle, the missing angle MOB. The missing angle MOB equals to the big angle AOB. This big angle AOB minus alpha. Again, the big angle AOB minus alpha equals to the missing angle. The big angle AOB is 90 degrees. So 90 degrees minus alpha equals to the missing angle. Again, 90 degrees minus alpha equals to the missing angle MOB, this missing angle. So the missing angle equals to 90 degrees minus alpha, but 90 degrees minus alpha equals to beta. Therefore the missing angle equals to beta. Okay, so then we focus on the right triangle OBM. In the right triangle OBM, this angle equals to beta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. So the missing angle must be equal to 90 degrees minus beta. But 90 degrees minus beta equals to alpha, therefore the missing angle equals to alpha. What is the length of line segment OB? Line segment OB starts from point O, that is the center of the quarter circle, and ends at point B, that is the point on the quarter circle itself. This is exactly the definition of a radius. Therefore OB is the radius of the quarter circle, that is equal to x according to our definition. Likewise, OA must be also the radius of the quarter circle, is equal to x, exactly for the same reason that OB is the radius of the quarter circle. So OA is also equals to x. In the next step, we proved that those two right triangles can go into each other. Why those two right triangles can go into each other? That is to say, the right triangle ONA is can go into the right triangle ONB. So why those two right triangles can go into each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to beta, therefore they are equal to each other. So we actually found out that all the angles of the right triangle on A are correspondingly equal to all the angles of the right triangle OBM, therefore, and finally, side OA of the right triangle ONA is equal to side OB of the right triangle ONB. They are both the radii of the circle that is equal to x, therefore they are equal to each other. So we actually found out that those two right triangles can go into each other according to angle side angle rule. What is angle side angle rule? Angle side angle rule is that if we prove that two angles and the side that included between the two angles in one triangle are correspondingly equal to two angles and the side that included between the two angles in a second triangle, then you actually proved that the two triangles can go into each other according to angle side angle rule. And here we proved that those two angles alpha and beta and the side that included between those two angles, that is side OA in triangle ONA, are correspondingly equal to those two angles that are alpha and beta, and the side that included between those two angles, that is side OB in the right triangle OBM. So, and therefore, again, that the right triangle, that the two angles alpha and beta, and the side that included between those two angles alpha and beta, that is side OA in the right triangle on A, are correspondingly equal to those two angles alpha and beta, and the side that included between those two angles alpha and beta, that is side OB in the right triangle ONB. Therefore, we actually proved that those two right triangles and that those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that side ON of the right triangle ONA is equal to side OMB of the right triangle OBM. Repeat again. Side ON equals to side BM. But we have already found out that ON equals to x minus 6. So we can write here that ON equals to x minus 6. And for this equation, x minus 6 equals to ON equals to BM. We will derive that BM is also equals to x minus 6. Side BM also equals to x minus 6 units in its length. Likewise, from the fact that those two right triangles can go into each other, we will derive that side OM of the right triangle OMB is equal to side AN of the right triangle ONA. Repeat again, OM equals to AN. But we have already found out that OM equals to x minus 3. Here, OM equals to x minus 3. So we can write here that OM equals to x minus 3. And from this equation, x minus 3 equals to OM equals to AN, we will derive that AN is also equals to x minus 3. This is side AN, and it is equals to x minus 3 units in its length. In the next step, I copied the right triangle AON in a new page, and we implemented on this right triangle AON the Pythagoras theorem. This is the right triangle AON that I copied from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle AON, it means that AO square equals to ON square, AO square equals to ON square plus NA square. Again, AO square equals to ON square plus AN square. OA, the hypotenuse OA is x, therefore OA square equals to x square, and it is equal to ON square. ON is x minus 6, therefore ON square is x minus 6 square plus AN square. AN is x minus 3, therefore AN square is x minus 3 square. In conclusion, we found out that x square equals to x minus 6 square plus x minus 3 square. So we opened the brackets on this side of the equation and found out that x square equals to x minus 6 square. X minus 6 square equals to x square plus 6 square, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 square. X minus 3 square equals to x square plus 3 square, that is 9, minus 2 times x times 3, that is minus 6x. So here we have x square on both sides of the equation, so x square will get cancelled. After cancelled x square, on this side of the equation we are left with nothing, that is to say 0. On the other side of the equation we have 36 plus 9 is 45, and we have also left with minus 12x minus 6x is minus 18x plus x squared. In conclusion, we found out actually that x squared minus 18x plus 45 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c, a, b, and c in this equation, in this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say x squared minus 18x minus plus 45 equals to 0, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. Now we have to put this data inside this general formula in order to find out the value of the values of x. X is the radius of the quarter circle. So according to this formula, x equals to minus b. b is minus 18, therefore minus b is minus 18, that is plus 18, plus minus square root of b squared. b is minus 18, therefore b squared is minus 18 squared, that is 325, minus 4 times a times c. So minus 4 times a is 1, so minus 4 times 1 is minus 4, times c is 45, so minus 4 times 45 is minus 180. In conclusion, we found out that x equals to 18 plus minus square root of 324 minus 180 over 2. So x equals to 18 plus minus square root of 324 minus 180 is 144 divided by 2. So x equals to 18 plus minus square root of 144 over 2. So x equals to 18 plus minus the square root of 144 is 12 over 2. So we found out that x equals to 18 plus minus 12 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12 over 2. 18 plus 12 is 30 and 30 over 2 is 15. So according to the first solution, x equals to 15 units in its length. And we also a second solution. We have also a second solution that is possible for x. According to the second solution, x equals to 18 minus 12 over 2. 18 minus 12 is 6 and 6 over 2 is 3. So according to the second solution, x equals to 3. But the second solution, x equals to 3, is incorrect solution. It is impossible that x will be equal to 3. Why? Because we have only found out that the length of line segment BM is x minus 6. So BM equals to x minus 6 units in its length. So BM is a length. Is the length of line segment BM. So BM is a length, it must be a positive number. And we know that the length of line segment BM is x minus 6. That is to say, x minus 6 must be a positive number, because it's the length of BM. That is to say, x minus 6 must be greater than 0. A positive number is a number that is greater than 0. So x minus 6 must be greater than 0. We add to this inequality 6 and found out that x must be greater than 6. If x must be greater than 6, x can never be equal to 3, but that is less than 6. Therefore, we cancel this solution, and we're left only with the first solution that is possible for x. That is to say, x equals to 15 units. Then I presented to you the formula for the area of any trapezoid. Quadrilateral ABCD is a trapezoid. Why? Because side BC is parallel to side AD. And the definition of a trapezoid is a quadrilateral with one pair of parallel sides. For that reason, quadrilateral ABCD is a trapezoid. What is the area of this trapezoid? Trapezoid ABCD. The area of trapezoid ABCD equals to the sum of its bases. That is, the two parallel sides are defined as the bases. So AD is the first base and BC is the second base. So the sum of its bases is AD plus BC times the height over 2. The height must create 90 degrees with the base. If CD creates 90 degrees with the two bases, those two angles are equal to 90 degrees, CD will be the base. If CD doesn't create 90 degrees with the two bases, we just draw perpendicular on one of the, either on AD or on BC, and the perpendicular will be the height to the base. Okay, for example, from BC, we draw perpendicular on AD, or we can also, from AD, we can draw perpendicular on BC. From any point on AD, we can draw perpendicular on BC. And the perpendicular will be the height to the base. So in conclusion, we found out that the area of trapezoid ABCD equals to the sum of its bases, that is AD plus BC, times the height to the base over 2. Again, the height to the base must create 90 degrees with the base. So what is the area of this green shape? The area of the green shape equals to the whole area of the big shape OBQSPA minus the area of this quarter circle AOB. Okay, again, the area of the green shape equals to the area of the whole shape, big shape, minus the area of the quarter circle AOB. And we have already found out that the area of this whole shape is equals to the sum of the areas of those two trapezoids. Trapezoid ABQS plus the area of trapezoid OSPA. And again, the area of the green shape equals to the area of the whole shape, the big shape AOBQSP, minus the area of the quarter circle AOB. We already found out that the area of the whole shape AOBQSP equals to the area of trapezoid OBQS plus the area of trapezoid OSPA. Why? Because of the fact that the whole shape consists of those two trapezoids, trapezoid OBQS and trapezoid OSPA. So the area of the green shape equals to the area of trapezoid OBQS plus the area of trapezoid OSPA minus the area of the quarter circle AOB. What is the area of trapezoid OBQS? The area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height, that is QS over 2. The area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height of the base, that is QS over 2. BQ is 3, OS is 15, QS is 9 over 2. 3 plus 15 is 18, 18 over 2 is 9, and 9 times 9 is 81. So the area of this trapezoid OBQS equals to 81 square units, plus the area of trapezoid OSPA. What is the area of this trapezoid OSPA? The area of trapezoid OSPA equals to the sum of its bases, that is OS plus AP, times the height SP over 2. Repeat again. The area of trapezoid OSPA equals to the sum of its bases, that is OS plus AP, times the height, that is SP over 2. OS is 15, AP is 6, SP is 12 over 2. 15 plus 6 is 21, times 12 over 2 is 6. And 21 times 6 is 126. If we already found out that the area of this trapezoid OSPA is equal to 126 square units, minus the area of the quarter circle AOB. The area of the quarter circle equals to the area of the circle over 4. The area of the quarter circle AOB equals to the area of the circle over 4. The area of a circle of radius x is pi x squared. So the area of the circle, that is pi x squared over 4, equals to the area of the quarter circle AOB. X is 15, therefore x squared is 15 squared, that is 225. So in we found out that the area of the quarter circle AOB equals to 225 pi over 4. 225 pi over 4 is 176.716 square units. So the sum of the areas of the two trapezoids is 81 plus 126, that is 207. That is to say, the area of the whole shape, that is the sum of the areas of the two trapezoids, equals to 207 square units, minus the area of trapezoid AOB, that is 176.716 square units. It will be equal to the area of the green shape. So 207, that is the sum of the areas of the two trapezoids, minus the area of the quarter circle AOB equals to the area of the green shape. So 207 minus 176.716 is 30.285 square units. In conclusion, we found out that the area of this green shape equals to 30.285 square units. Okay, thank you very much.